Hey y'all, today we're going to look at continuing our lessons or our unit on exponential functions by looking at exponential growth and exponential decay. So by the end of this unit or this lesson, you should be able to write exponential growth functions and evaluate them. So write and evaluate these functions. So exponential functions we learned last week are those functions that increase or decrease by multiplying by a particular value, not by adding or subtracting like we do with linear. And so if you remember, they have that curved shape that looks like this. And so it's exponential growth when you see that curved shape that increases when you go from left to right. If you see that curve decrease from left to right, then you're talking about exponential decay function. But there's still functions that increase or decrease by multiplying by a certain amount. And they're all still written in the form a times b to the x power. We learned that last week too. So we're going to look back at some of that today and then look at how to apply that to some scenarios where we're seeing growth or decay in a situation. So exponential growth or exponential decay occurs when an amount increases or decreases by a certain percentage over a period of time. So it increases or decreases by a percent over a period of time. So in that, when you're looking at one of these growth or decay functions, the factor that you multiply by is all based on what that percentage is. So when it's an exponential growth function, that factor is going to be greater than 1. If it's an exponential decay function, that factor is going to be somewhere between 0 and 1. And look, I put than in here, and I really didn't mean to do that. So, let's fix that. Between 0 and indicates decay. So that's saying if you have something like 1.25 as your factor there, you know that that's growth because that's a number bigger than 1. If you have something like 0.75, that's going to be decay because that's a number that is less than 1. So that's what we're looking for there. If your number greater than 1 or less than 1, that's going to determine whether it's growth or decay. So something like 1.25 would be growth. 0.75 would be an example of decay. So exponential growth functions are all built in the same format as normal exponential functions. So we're still dealing with those functions that are written in that a times b to the x. So remember, in that a represents your y-intercept or your initial value. And b represents your factor. But you're not going to be able to just immediately know B in these problems. They're going to have to find B using the percentage that they give you and the information that they tell you. So the problem is going to tell you that it's either growing or decaying, and it's going to give you a certain percentage amount. So if you have a problem like that, the first thing you want to do is change that percent to a decimal, because we can't use percents in our problems. Percent can't go into an equation. You've got to turn it to a decimal first. So 2 ways you can do that. You can either divide it by 100, or you can just move it 2 spaces to the left. So here's what I mean by that. If you're looking at something like 25%, 25 divided by 100 would be 0.25, which is the same thing as taking the decimal that would be on the back of 25% and moving it 2 steps left and putting it here, 0.25. So whether you divide it by 100 to get there or you move the decimal 2 steps to the left to get there, it does not matter to me. But you need to make sure the first thing you do is change a percent to a decimal. Then if it's growth, exponential growth is occurring, you're going to add that percentage to 1. If it's exponential decay, you're going to subtract the percentage from 1. So let's say it tells you that the function is growing by 25%. You do 1 plus 0.25 to get a factor of 1.25. If it tells you it's decaying by 25%, you do 1 minus 0.25 to get a factor of 0.75. And the reason we do that is because if you decay 25%, you're left with 75% of what you started with, because everything starts at 100. If you grow 25%, then you're at 125% of what you started with, because everything starts at 100. So when it's growth, you're at 1.25. When it's decay, you're at 0.75 for your factor, because that's the amount of the whatever it is you have left. All right. So let's look at some examples of this. So we're going to write some exponential functions based on these descriptive scenarios here. So each one of these tells me the value that we start at, and then it tells us a growth rate or a decay rate percentage. And so with all these percentages, the first thing we want to do before we ever try to write a function with this is change those percents to a decimal. So my growth rate of 5%, I'm going to change that to a decimal and make it 0.05. And again, we can do that by dividing it by 100, or you can just pick up the decimal that is behind the 5 and move it 2 steps to the left. Doesn't matter to me how you do it, so long as you can come up with it. So we're going to imagine dividing by 100. So for 25%, same thing. I'm going to divide it by 100 and get 0.25. With 0.005%, divide it by 100. I'm going to get 0.0005. Yes, I know that's a weird number. It is what it is. And then 99.9%, same deal. I'm going to divide it by 100 and get 0.999. Okay. So those are going to be the numbers that we use. Now, they're not necessarily going to be the numbers that go into our problem, but we're going to use those to either add or subtract from 1 to be able to create the function that we need. So again, when it's a growth function, we're going to add to 1. When it's a decay function, we're going to subtract from 1. So growth, 1 plus that, decay, 1 minus that. This next one will be growth, so we'll add it. This next one will be decay, so we'll subtract. And so when I go to write these functions out, I'm going to start with my initial value. In parentheses, I'm going to put my new factor. So 1 plus 0.05 will be 1.05. And then my x. So the second one is decay, so I'm going to subtract it. So I still start with 25. But my number in parentheses will be 1 minus 0.25, which is 0.75 to the x. For C, it was a growth function again, so I start with my 150. I'm going to add 1 plus 0.0005 and get 1.0005 to the x. And then for my last one, my decay function here, I'm going to subtract 1 minus 0.999, and I get 0.025 times 0.001 to the x. So again, we're writing these functions based on the information that's given here. Everything is changed to a decimal, and then we're going to add to 1 for growth and subtract from 1 for decay to get the factor that goes in my parentheses here. The front number is always... The number in the front is always your initial value or your y-intercept, and this will always be your factor, but you can't just use the factor as the percentage. You have to change it to use it.
We need Austin Buckarell to the front office for checkout. Austin Buckarell to the front office.
All right. Now let's look at these. These want us to do the same thing, but now we're going to determine whether it's growth or decay, and then determine the actual growth or decay rate. So we're basically going to do what we just did, but in reverse. So we know we can look at these functions and automatically know if they're growth or decay based on what the factor is. Because earlier we talked about how to grow, you're going to have a factor greater than 1. And to decay, you're going to have a factor less than 1. So greater than 1 is growth, less than 1 is decay. So when I look at these and I see 1.06, I automatically know that's growth because that's a number bigger than 1. 0.86 is decay, smaller than 1. So 2.15, bigger than 1, it's growth. 0.06 is smaller than 1, so it's decay. Now, since every percentage that we worked with in the past problem was based on a starting value of 1 or 100%, we've got to consider that everything that's in parentheses here represents that 100% plus or minus whatever the growth or decay rate was. So to be able to figure out what that rate is, we want to take these numbers and start out by subtracting the 100% from it. So we're going to subtract 1 from every rate that's given to us so that we can see what was left to be the growth or the decay. So 1.06 minus 1 leaves me with 0.06. 0.86 minus 1 leaves me with negative 0.14. 2.15 minus 1 leaves me with 1.15. 0.06 minus 1 leaves me with negative 0.94. Here's what I know from that information. So these are all my growth factors or decay factors still in decimal form. I need to change them back to percentages so we can actually tell what the growth or decay rate is. But this is what the growth or the decay part of it, not including the 100% from the original, but this is what the growth or decay part was outside of that. So this 0.6 that I have for A represents a 6% growth because 0.6 is the same thing as 6%. And you can find that by moving the decimal back to the right 2 steps or multiplying that by 100 to get it back to percentage form. So it's just reversing what we did on the previous problems where we divided by 100 or moved it to the left. We can either multiply by 100 or move it to a right to change it back into a percentage for our description here. Now this decay, or this negative 0.14 tells me that this decayed 14%. We're not going to write it as negative 14 because we have the word decay there. But the fact that it was negative means that it was decaying 14%. This 1.15 is again a growth factor of 115%. This 0.94 is a decay factor of 94%. So those decimal values that we get when we subtract 1 become the percentages that we are growing or decaying by. You do have to turn it back into a percent by multiplying. So if you want to go from a decimal to a percent, you're going to divide by 100. To go from a percent back to a decimal, oh, I did that backwards. To go from a decimal to a percent, you do times 100. To go from a percent back to a decimal, you divide by 100. So remember, the decimal form is going to be smaller than the percent form as far as your number is concerned. All right. So take a minute and pause this video, and I want you to see if you can write a function based on the information given to you here. So this is what we did in the first slide of examples. And then see if you can look at a function that's given to you and tell if it's growth or decay. So circle one or the other, and then tell the initial value and the growth or decay rate as a percentage here. So this should be, when you give these answers, these should be percentages. But pause the video and see if you can get those worked out, and then come back and see if you were correct. If you haven't paused the video, pause the video now. All right, so that should have been long enough for you to look at those 4 little questions there. So in the first 2, you should have started both functions with your initial value here and here. And then here, you would have added that to 1 or subtracted from 1, depending on whether it was growth or decay, to get your numbers here, and then you got a value of x. And then for the second two, you had growth happening here because it was bigger than 1, and decay happening here because it was smaller. When you subtracted 1 from both of those, you got a growth rate of 104% and a decay rate of 95% for both of those. And again, your starting value was here and here. All right, if you miss any of those, make corrections where you need to, and then let's roll on. So now let's look at some examples of word problems with this stuff, because this is typically how you're going to see this, where you're going to be given a word problem and it's going to tell you that something either increased exponentially or decreased exponentially or something like that. So you're going to usually be asked to write a function. They might ask you for other information about it. They might ask you to use the function to find the value of something somewhere in there. So this one says, Ava sells a painting for $1,400 and its value increases by 9% each year after it is sold. Write an exponential growth function. So they tell us it's growth. We knew that anyway because it said increased by 9%. But exponential growth function to model this situation. Then they ask us for domain and range of it and for what the y-intercept represents. Then they ask us to find the value of the function in 25 years. So I've kind of laid all this out here so that we know exactly everything we're supposed to talk about in our answer. But to start with, let's write our function. So if the painting started out at $1,400 and then it increased by 9%, that 9% is 0.09. And because it's an increase, we're going to add that to 1. And then our x. So when you're thinking about domain and range for these functions, you've got to know what the function represents. In every exponential growth or decay function, the domain is always going to represent time. The range is going to represent whatever the function is about. So for this function, it's the value of the painting. So when you think about time, time can never be negative. You can't go back in time. So time starts at 0 and goes on forever. Never stops. The value of the painting, though, started at $1,400. And we don't know how much it will be valued later, but we know it could continue to grow in value forever. The y-intercept for this function is that 1,400, and that represents your starting value. Now, to figure out the value in 25 years, remember x is always time. So this 25 represents your x at 25. So you could put this in Desmos and go find where the x value is 25. Or faster to me to just plug in 25 for the x up here and calculate that with your calculator. So if you do 1,400 times 1.09 to the 25th power. So we get a value of 12,072 and 31 cents. So for these examples like this where it's a word problem, you're typically going to have to write a function and then use that function. Sometimes they'll ask you other information about it too, but usually just writing it and then using it by substituting the value in for x or for y. And I know up here for range we said that represented y, but we didn't actually write a y in our function. All of these functions can be y equals that value. We just left that part out. All right, let's keep going. So this is very similar, but we don't have as much to answer about this one. Samaya purchased a sculpture in 2014 valued at $1,200. It's increasing at a rate of 8%. Write an exponential growth function to model the situation, and then find its value in 2022. So again, our function is going to start with our starting amount, and then show our percentage, our growth factor. If it's increasing at 8%, that's 0.08. Again, we divide that by 100 or we move the decimal twice. So since it's increasing, 1 plus that, that's going to be my function. So the value in 2022, not in 2022 years, I made a typo there, yeah, but in 2022. that function's, or that sculpture's value in 2022. Remember, if your X represents years, 2022 is 8 years after 2014. So our X is going to equal 8. We're going to put 8 in up there. I don't know what happened here, y'all, but I think my pen is dying. Sorry, y'all, I had to go get a stylus. A different stylus, anyway. Maybe. Okay, I think I got my writing issues worked out. So 1.08, and then we're going to substitute in for X and 8, and we're going to calculate that. And again, you can do that in Desmos, but I really think it's probably faster just to throw it in your regular calculator. You can also just type it in Desmos like that, and it'll give you an answer. So we get that this sculpture would have a value of $2,221.12. 2,221.12. All right. Let's look at another one now that's going to be decreasing. So it says the population of Trevorstown is decreasing at a rate of 1% per year. So we know it's going to be exponential decay. Here's my rate. In 2010, there were 1,300 people. Write an exponential decay function to model this, and then they ask us to find the population in 2016 and describe the domain and range and the y-intercept of all of this. So again, to write our function, we need our starting value, which is 1,300 people. And we need to figure out, using our rate, what our factor will be there. So if it's decaying at 1%, that's 0.01. It's decreasing, so we do 1 minus that, and we get 0.99 to go in place of our factor. So to figure out where it would be in 2016, if it started in 2010 and we're going to 2016, that means we're looking at where our X would be 6. So I'm going to do 1,300 times 0.99 to the 6th. Until I get a value of $1,223 people, or really 1,224 people. So it comes out to be 1,223.924194. But because it's people, we'll round to a whole number. So 1,224 people. Now let's look at domain and range for this function. So remember, with exponential functions, domain is always time. So time can go on infinitely. So that means X can approach infinity, starts at 0. The range, though, the number of people in the town cannot go on indefinitely. Since it's decaying, the fewest people they could reach is 0. The most people they have is 1,300. And then the y-intercept is our 1,300 people they started with. All right, let's keep going. So this one's similar to that one, not as much to answer. Turnbow studied the fish population in the pond near his house. He found that it's decreasing at a rate of 3% per year. The original population was 48,000. Write an exponential decay function and then use it to predict the population after 7 years. So again, we write our function starting amount, and then we're going to put in our factor here. So if it's decreasing at 3%, 3% is 0.03. We'd subtract that from 1. and we get 97% or 0.97 as our factor. I made a typo here too because I was copy and pasting too quick. But we're trying to find the value after 7 years. So that means I'm going to replace x with 7 and calculate that. So 48,000 times 0.97 to the 7th power gives me a total fish population of 38,783. It says 0.17655, but again, because it's fish, we're going to round it to a whole number. 38,783 fish remaining in the pond after 7 years. All right, let's keep going. Now this one asks us to decide if this is growth or decay and then to write a rule for it. So looking at the shape of this, remember we read graphs from left to right. So if we're on the left side of this and going to the right, this is going down. You see that's decreasing. So this is exponential decay. If we're writing a rule for it, we need 2 points. If you remember us doing that in the last lesson from this. We know our starting value. But to get what goes in parentheses, we've got to have 2 points so that we can calculate the value from those two. So looking at this graph here, I can pull the point at 2. And then I can use the point right next to it at 1. They've got to be 2 consecutive points. So I have this point at 0, 2. And I have this point at 1, 1. Okay, so I have a point at 0, 2, I have a point at 1, 1. To find the number in parentheses, I take the second y and divide it by the first y. Not the biggest and the smallest, but the second one. So this is the second one. This is the first one. Divide the second one by the first one. So I get a factor of 0.5. That means that this is an exponential decay function representing 50% decay. And I know that because that 0.5 is 0.5 away from 1. And that 0.5 represents 50%. Okay. Now here we have another one involving some graphs. And so we're going to write an exponential function for each of these stocks that are modeled here. And then talk about what that means about their value. So from the graph over here, you can see that stock A is decreasing exponentially, while stock B is increasing exponentially. So we're going to write a function for both of those and then compare what's actually going on between these two. So for stock A, we see that it starts at 16. And then we need to look at how that's changing from that point to the very next point at 1. I'm going to use this point right here at 1. And we see that it goes from being at 0, 16 to being at 1, 12. And so we'll divide 12 by 16 to get our factor there, which is 0.75. So 0.75 goes here, and my x goes up here. I'm going to go and do the same thing for B. So for B, we see that B starts at 5. And then by 1, we're up to 6. So to get my factor there, I'm going to do the second y divided by the first one and get 0.2. I'm sorry, not 0.2, 1.2. So if they ask you to compare the behaviors of the two stocks or describe and compare them, then we're going to say that this first stock is decaying or decreasing by, and let's be specific about how much it's decreasing by. If our factor is 0.75, remember we subtract 1 from that and that tells me the decay rate. So that means it's decreasing by 25%, because 75 minus 1 is 0.25. And then for stock B, we know that it's increasing, it's growing. And we'll do the same thing there. We're going to subtract 1 from it and get 0.2, which is 20%. So growing by 20%. So these numbers that we're getting here are all based on how far that number in parentheses is away from 1. So subtract 1 from it to see its distance from 1, and that's going to tell you whether it's decaying or growing and by how much. All right, moving along. So there are a few left here now for you to try. I think there are 3 slides of you try it. I'd like you to pause the video, take a few minutes and try to work those 3 out. And then come back and see if you were correct. The 2 on this slide just ask you to write a function and evaluate it. And then the next one kind of does the same thing. And the last one is one similar to the stock question we just did. So take a few minutes and work through those. And then when you have finished all 3, come back to this video and see if you were correct. All right, take a look at these now that you've had a chance to work at them, and see if you got the same thing that I got for both of these on the first slide. So I wrote my function using the value that they gave me as a starting amount, and then using my percentage, added to 1 for this one and subtracted from 1 for this one to get my overall function. And then I evaluated it for the number they gave me. So evaluated it at 4, evaluated it at 10, and got these numbers here. Now, since they were both money, I rounded to the nearest cent, so 2 digits past my decimal. If they were things that could not have been decimal values, then I would have gone to whole numbers. But because it was money, we could do that. If you missed any part of that, pause the video and make corrections to what you need to. Take a look at what I did that was different than what you did and see if you can figure out where your mistake was there. And then on the next one, I did the same thing basically. She had started with $14,000 in the account at a 4% interest rate, so I added that to 1 to show that we would be adding growth for that, and then evaluated it at 15. And again, because it was money, I went to the nearest cent and rounded it to 0.21 cents there. And then this last one was a little bit tougher because you had to write your functions from the graph there. So you had to find your starting value for each one. Parcel A started at 70,000, parcel B started at 35. And then you had to calculate your growth rate by taking the y's and dividing the second y by the first y. So for parcel A, I did 60,000 divided by 70,000, and I got about 0.86. For parcel B, I did 35,000 and 40,000. 40 divided by 35 gave me about 1.14. And so what I could see from that is that parcel A was decaying by 14% when parcel B was growing by 14%. And I know this was decaying by 14 because this is 14 away from 1. This was growing by 14 because this is 0.14 away from 1. All right. Now we're going to look at some of these test prep style questions. So we need to be able to see how this is going to be evaluated on our test and use that information to or use what we know about exponential functions to be able to answer these kinds of questions. So this one says, the amount of medicine in a patient's bloodstream is shown by the function A of h equals 600 times 0.75 to the h power, where h is the number of hours that have passed since the medicine was given. What does the 0.75 represent in that function? So looking at that, we know it's exponential. Specifically, we know it's exponential decay because this number right here is lower than 1, and we know multiplying by something smaller than 1 will cause exponential decay to occur. So the 0.75 represents the amount that it is decreasing by. It is not increasing, so it could not have been either of these. But it's decreasing, but not by 75%. That 0.75, remember, to figure out the percent of decrease, we subtract 1 from it, and we get negative 0.25, which tells me it was a decay rate of 25% per hour. So B is our best answer for this. You will never use the percentage that's in the problem as the percent, or the number in the problem as the actual percent. It's always got to be added or subtracted from 1. All right, this one asks which scenario is best to represent exponential growth, exponential decay, or neither. So to be exponential growth, you have to have something that's multiplying or increasing by a percentage every time. For exponential decay, you have to have something that's dividing or decreasing by a percentage every time. And if it's neither, it's not doing either of those things, then you would call that neither. So this first one says an initial population of 15 hamsters doubles each year for 6 years. Double means multiplies by 2. Multiplication means that we've got something that is exponential. So since it's getting bigger, exponential growth. Sheila bought a car for $18,000. She expects it to lose value at a rate of 14% per year. Losing values decreasing by a percentage means it's exponential decay. Ella starts a track program by walking 2 miles. She increases her distance 3% each week. Goes up by a percentage. It's exponential growth. To take a taxi, it'll cost Connor $2 for the first mile. After 5 miles, it will cost him a total of $6.50. Nothing about this involves a percent or multiplying by a certain amount. This is neither. And this one says membership at the fitness center declined at a rate of 5% per year. That's going to be exponential decay, decreasing by a percentage decay. All right, this next one. Sam has 3,250 followers on social media. His number of followers is decreasing at a rate of 3% per week. Which function represents the number of followers after W weeks? So decreasing means we're subtracting from 1, which means my factor is going to be 0.97. This W versus the W minus 1 thing, we're going to do sequences soon. And sequences involve this minus 1 exponent. But nothing we have done so far has involved that. So we know it's not this or this. And because it's decreasing, we have to choose A. We'll only use the minus 1 notation for sequences, and this is not a sequence. It will specifically say sequence. And we'll see that later on. All right. The population of a particular bacteria is said to grow exponentially. What does that mean? And so it says it grows by a constant percentage. It grows by a constant percentage before decreasing at a constant percentage. It grows at a constant rate. It grows by a constant rate before decreasing by a constant rate. Exponential always involves percentage. If it's growing, it's increasing by that percentage. Grows by a constant percentage. This that grows by a percentage before decreasing at a percentage, that would be a situation of probably a quadratic. And this one that's growing by a constant rate before decreasing at a constant rate would be an absolute value function. This one that just grows at a constant rate would just be linear. So the only one that would work there would be A. And then this one gives us this function, and it says this equation represents the number of bacteria present after H hours, or H hours after an antibacterial medication is applied. Which statement is true? The amount of the substance decreases by blank percent each hour. So when you look at this, you know the part that tells you how much it's decreasing is the 0.87. But it is not decreasing by 87%. To find how much it's decreasing by, we've got to subtract 1 from that, and we get negative 0.13. That tells me it's decreasing by 13% each hour. Remember, when you get this decimal, to change it back to a percent, you can just multiply it by 100. And that's where we're getting our percentage from. The negative part doesn't matter. That's just the thing that told me it was decreasing. All right, that is the end of this lesson. And make sure you submit those notes and have a beautiful day.